Welcome to myprojectbazaar.com. Now we discuss about the product for fast design space exploration using Vivado HLS non-binary LDPC decoders. Next we see the abstract for the product. FPGAs are increasing becoming components of heterogeneous systems such as the data centers or battery powered devices. However, FPGA strength comes with a shortcoming. It is hard to maintain the flexibility of architecture designs while offering the productive programming model. While HLS tool offer a high-level programming interface and solid hardware understanding is still required, not only to allow the instruction of optimization to be successfully applied by the compiler, but also so that the efficient hardware is generated. In this paper, we show how to perform the fast design exploration of an LDPC decoder over a non-binary representation in Galileo's field equations using the Vivado HLS. To achieve this, we refactor the code and to introduce the directives that allow the exploring parallelism such as the unrolling and pipelining of loops to achieve high throughput performance again. The LDPC decoder architecture based on FFT SPA is structured into different kernels composed of double or triple nested loop body functions. The optimizations carried out consist of moving all intermediate results from DRAM computations to BRAM defined arrays. Array partitioning to expose more read and writing ports and increase the bandwidth. Computing a field programmable gate array has been receiving continued interest as it provides has performance at relatively low power budgets, while avoiding the high non-recurring engineering codes associated with ASIC designs. However, FPGA development is typically performed using the register level transfer language, which make the design process protected and error prone when compared to software design flows. To ease this problem, high level synthesis tools has been introduced which abstract away the RTL architecture descriptions from the designers. In this work, we explore the design space of non-binary Galileo's field low-density parity check decoder using Vivado HLS and compare its data for RTL designs. Next, we see the flow diagram for the product. The input data bits to passing the shifted serial bits. The shifted serial bits based on the Galileo's field equations and the equation model functions to be shifted and XOR function to be presented in the shifted serial bits and the parity bits to be implemented in the XOR functions and bitwise differentiation to be analyzed by each parity bit representations. Randomized, we select the shifted serial bits output and to apply the parity bit architecture. If consider the parity bit architecture and to analyze is all 0 as no error to be presented and the function to be completed. If no, the error to be presented in any one of the parity bit and to produce the no one conditions and to satisfy the no elements. If the parity bit is the first set to be sent true, this condition to be compared with two kind of things. If the condition to be satisfied is yes and to correct the bit. If the condition to be not satisfied in uncorrectable error and to passing the message to the output data bits. This function to satisfy the low density parity check architecture and this final architecture to perform with Vivado HLS software. This software to identify the different kind of RTL design development view for overall functionality development. This Vivado HLS software to perform the high-level synthesis operation for based on the RTL design and development based works. These bits to used to the error detection, error correction performance for overall data encoding and decoding operation. LDPC is the most important processing for overall encoder based error detection and correction operation, and the decoding side also implement in the LDPC decoding architecture. We focus only the LDPC decoder architecture and how to perform the error correcting performance in our the HLS software. Next we see the final output for the product. This is the Vivado project file. Just you open the LDPC decoding architecture performance. Generally, we implement the basic LDPC structure based on the majority logic and the parity function for bit differentiation and to correct and detect the error performance for overall decoding operations, but we implement the new software for Vivado HLS functions. These functions to implement the high-level synthesis performance for real-time designs. So the real-time designs, we implement the RTL design development based on our functions for overall Vivado based process. You just open the LDPC decoding functions for overall generating files. These files to create the output functions and to open the SR behavioral model and to produce the programming model for overall LDPC decoding architectures and to simulate the simulating model for overall run simulation based process for based on the simulation work we analyze the how to work with the LDPC decoding architecture burst based on the processing work if the conditions to be satisfied and to analyze the waveform file for overall architecture. These are the LDPC decoding function for initial output data bits. Then we go to the RTL dynamic representation. So we run the open elaborated designs and we see the final RTL designs in detailing. This is the final output for the overall LDPC decoder architecture in the HLS software. This is our final RTL diagrammatic representation for overall LDPC decoding architecture. These the net files and all the input and output details to be presented in overall functions and to identify the input and output functions, net function and instant functions for overall architecture functions. These are the main and gain level and all the things to be produced by overall output based process. This function to represents all the designs and development for overall architecture based process. This is the final output.